Hi, everyone. My name is Eleonora Isotta, and I'm a postdoc at Northwestern University. And in this video, I'm going to present our article, Heat Transport at Silicon Grain Boundaries, that was recently published in Advanced Functional Materials. We're interested in the problem of grain boundaries and how they modify heat transport because it can be very relevant for a number of applications where controlling heat transport is critical. And one of the applications that we have in mind is thermoelectrics. A thermoelectric device is capable of converting heat into electricity and vice versa. And to have a high performance device, we need to have a high figure of merit, ZT, of the constituent materials. So there are a number of factors that go into the ZT, but one of them is the thermal conductivity. And normally, we want to have as low as possible of a thermal conductivity. And that's why researchers have been using microstructure and grain boundary engineering for suppressing the thermal conductivity. And really countless are the studies in the thermoelectric field that have been exploiting grain boundary engineering for suppressing the thermal conductivity and improving the figure of merit. However, most of these studies focus on bulk properties and bulk measurements, which effectively treat the sample as homogeneous. And if they have to derive the effect of, for example, grain boundaries, they would, for example, measure the bulk properties as a function of grain size or as a function of grain boundary type. But that's still a homogenizing picture. Instead, we don't really have a good idea of what happens locally in the vicinity of a grain boundary. And only recently, local studies have become available in the literature. And for example, fairly recently, this group used a technique called time domain thermoreflectance, or TDTR, to perform a thermal conductivity image of a sample of polycrystalline diamond. So what they saw was fairly interesting, and they saw that a sample is far from being homogeneous. In fact, they did see some local suppression in thermal conductivity in regions with a high density of grain boundaries as opposed to the center of large grains. And we also recently worked in the area of thermal conductivity imaging, where we have been employing an analogous technique called frequency domain thermoreflectance, or FTTR. And the first material we have been working on is tin telluride, and you can find the article over here, where in essence, this is what we obtain. So these are thermal conductivity images collected in the areas marked by the squares. And we do see some local suppression in thermal conductivity right around the grain boundaries. So again, the picture is of a material not being homogeneous. And we do see that this suppression extends for a few microns. And this is already quite interesting because if one thinks about classical models for thermal conductivity, for example, Callaway-Clemens models, one would indeed think that a lower grain size should be conducive to a lower thermal conductivity by virtue of the fact that a limited size limits the phonal mean free path. However, this thermal conductivity would be applied all over the sample pretty much with the same value. Instead, we do see that the picture is inhomogeneous. We do see some local suppressions, and these seems to be also spanning a few micron widths. So in short, from this study, there are two main takeaways that I wanted to mention. So number one is that we do see that different boundaries behave differently. In particular, we saw that low misorientation angle boundaries show a lower suppression compared to high misorientation angle. The second key takeaway is that we wanted to have a unique parameter to characterize each boundary to facilitate comparison and also to have an estimate of the thermal resistance. And we do so by using a Gibbs excess approach. In short, if we take a cross-section of a thermal conductivity image, we would expect the thermal resistivity to be constant in the grain, locally increasing at the boundary, and then constant again. So we take our excess boundary resistance as the integral of the excess resistivity, basically the local value minus the constant value in the grain. So this blue area over here, or whatever is in excess compared to what expected in the grain. And we have calculated this excess thermal resistance for all the boundaries in tin telluride, and we do see that high misorientation angle tend to show a higher value compared to lower misorientation angles. And this seems to be quite in accordance with the grain boundary energy, which is also known to increase with the grain boundary misorientation angle. Okay, but let's move on to what is the core content of this article, that is thermal imaging in silicon. And we're interested in silicon specifically because it's a material with a number of technological applications, and because grain boundary effects are supposedly very strong. And for example, from the data in this article, we can see that if we introduce a grain size in the order of hundreds of nanometers, we should expect a strong suppression in the bulk thermal conductivity, almost up to 1 order of magnitude. And this should correspond to a thermal resistance of the grain boundaries in the order of 2 to 5 meter-square Kelvin per gigawatt. So for this study, we decided to adopt a sample of multicrystalline silicon, that is silicon with millimeter-sized grains. And we identified an area of interest and performed an EBSD, or electron backscatter diffraction, to identify the local orientation and see where the grain boundaries are. And we found a grain boundary of interest. This in particular was a high angle grain boundary, and performed the thermal conductivity imaging across this boundary. So this is the first result that we got. And we do see some suppression crossing the diagonal, that is basically where we would expect the grain boundary to be. However, it is a very faint suppression. So it was quite unexpectedly faint compared to what we were seeing in tin telluride. So to try and understand why this was happening, we went back to the EBSD and analyzed it a little bit more carefully. And what we saw is that the majority of the boundaries present in this image were actually a special type of boundaries, namely coincident side lattice ones. So what does this mean? So just to give you an idea, so if we imagine to have one lattice on one side of the boundary and to prolong it indefinitely onto the other side, then for some geometrical configuration, we would have some of the atoms of the first lattice that overlap with the second lattice. So if 1 out of 5 of these atoms overlap, then we call this a sigma 5 boundary. And this is at the origin of the CSL, coincident side lattice, or sigma classification. So the smaller the sigma number, the more the overlap, the more symmetry the boundary has. So what I told you earlier is that the grain boundary energy is known to increase with the grain boundary misorientation angle. And this is generally true. However, some grain boundaries, namely the coincident side lattice ones, are known to defy this trend, and their energy drops almost to 0 in some instances. So from this, we can already start having a clue of what was happening over here. So we're having, so the boundaries that we are probing are extremely low energy ones. So that might start explaining why we see such a low thermal conductivity suppression. So with this in mind, we decided to proceed and probed a number of different boundaries with different sigma numbers, different shapes. And we generally see some suppressions corresponding to the locations where we would expect boundaries to be. For example, this one here, over there, and so forth. And we see that this suppression seems to vary a lot from boundary to boundary. So we have been using the same Gibbs excess approach to extract an equivalent excess boundary resistance. And just to put everything into a unique plot, this is the excess boundary resistance as a function of sigma type of the boundary. So we can notice a few things. So number one, most of the boundaries are clustered around this resistance value of 0.5 meter-square Kelvin per gigawatt, which if we compare, so we don't really have experimental reports in the literature for individual boundaries. However, we do have molecular dynamic studies, and most of them are indeed on sigma type boundaries. And we can see that the reports are relatively in agreement in terms of order of magnitude with what we are observing in this sample. So other reports are around 0.5 or 1 meter-square Kelvin per gigawatt. The other interesting thing that we notice about our experimental results is that, for example, for sigma 3 boundaries, we notice a very large spread of the excess resistance over more than one order of magnitude. And this is important because sigma-3 boundaries all have the same misorientation angle. So this thing is happening with the same misorientation angle. So we decided to take a closer look at the boundary showing the lowest and the boundary showing the highest resistance to try and understand why we are observing this. So among the boundaries showing the lowest resistance were this sawtooth-like boundary, where interestingly, we do see that one edge of this cusp, namely this one over here and this one over here, seems to be faint but visible, whereas the other edge seems to be not visible at all. So in this area, we decided to perform a higher resolution EBSD. And what we could start to notice was that one of the edges seems to be more like a straight line, whereas the other one seems to have some facets. So to be able to confirm this, we took TEM, transmission electron microscopy lamella, that was crossing both the boundaries, so containing both of them. And here is the transmission electron microscopy on that lamella. So what you can see is that even from the TM, we can now more clearly see that one of the boundaries is extensively faceted and rough, whereas the other one is a smooth, clean interface. So we think this is relevant. In fact, the boundary showing a rough interface is the one associated with a higher resistance. And so in this case, the difference in roughness might explain the difference in the behavior that we are observing. Okay, but then what about the higher resistance boundaries? So these again are sigma-3s and showing an even higher resistance. So what is happening in this case? So for these boundaries, something interesting to notice is that from the EBSD picture, we would expect just one boundary to be present. However, from the thermal conductivity image, we could see multiple lines of thermal conductivity suppression pretty much parallel one with another. And again, we decided to take a TEM lamella crossing this boundary. And what we can see from this lamella is that we spot a number of different boundaries clustered in this region. You need to consider that this whole lamella spans across this region. So whatever we had identified previously in the EBSD as one boundary is actually a collection of multiple boundaries closely spaced with one another. So it's a case of nanotwinning. In fact, the average spacing that we identify for this boundary is around 20 nanometers. And so in this case, we think that having many boundaries clustered very close to one another is actually the reason why we see a higher resistance. This is an effect of multiple, not just one boundary. Okay, and another legitimate question that one might have is, what is the impact of the angle of the grain boundary plane? So the angle between the plane of the grain boundary and, for example, the sample vertical, because that also is something that may change from boundary to boundary, and that might affect the Gibbs success estimate of thermal resistance. So to address this question, we decided to build a finite element model of a grain boundary, and to basically simulate a FTTR experiment by scanning a heat source, replicating the experiment in the finite element model, and extracting the equivalent, the corresponding thermal conductivity profile as a function of the angle theta, where theta is the angle between the grain boundary and the sample vertical. And this is the result that we obtained. And if we use the Gibbs success approach onto this thermal conductivity profiles, we would obtain this trend of excess resistance with theta angle. So again, angle between grain boundary and the sample vertical. So we do see that indeed the resistance estimate changes, and the effect seems to be minimal below 45 degrees, whereas it seems to be more accentuated afterwards. So is this impacting the comparison that I presented in the previous slide? So for the boundaries that we have analyzed with TM, we could verify the angle from the TM lamella, and the angles were all below 45 degrees. So in the region where we do not expect to see a change of the excess boundary resistance with angle. So comparisons should hold. The only exception was for the rough versus the smooth boundary. In fact, for the rough one, we saw an angle of 15 degrees, whereas for the smooth boundary, we saw an angle of 70 degrees. So based on the theta angle alone, we would expect the boundary with 70-degree angle showing a higher resistance. So the fact that this boundary still shows a resistance of 0 means that the roughness effect is what is dominating the contrast in this case. And just for completeness, have this, let's say, this framework could enable us to answer another very important question, that is, how is the Gibbs success estimate supposed to relate to the classical thermal boundary resistance estimate? So to do so, we built another simulation where the boundary was instead parallel compared to the heat source, and also parallel compared to the sample surface. And this is a classical configuration that one uses for determining the thermal boundary resistance of an interface. And if we calculate, if we run the simulation, we would obtain a value that is higher than the excess boundary resistance. So with this in mind, we think that, at least based on the finite element simulation, there might be a factor of 3 between the resistance offered by a vertical boundary and the resistance offered by the same boundary but placed horizontally. Okay, so now we can draw some overall conclusion on what we saw, and basically the differences that we were seeing for the sigma 3 boundaries are rooted in distinct morphological variations of this boundary. In fact, we can see that a smooth sigma 3 offers a resistance that is basically 0, whereas whenever we introduce roughness, this value seems to increase to in the neighborhood of 0.5. And however, the highest values that we observe are for nanotwin boundaries. So whenever there are multiple boundaries present at the same time. And additionally, we saw that also the angle that the boundary forms with the sample vertical can impact the estimate, and can also be one of the reasons why we see a spread in our results. Okay, so but this picture was for coincident side lattice boundaries. What happens instead for more random boundaries? So just to be able to answer that question, we produce a sample with spark plasma sintering to have a more random distribution of grain boundaries, identified some random ones, and performed some thermal conductivity imaging around there. And we can see a much more marked suppression of thermal conductivity corresponding to significantly higher values of excess resistance. And this is not the only interesting thing. The other interesting thing about this measurement was that we could notice that resistances were higher, but also much more fluctuating compared to, for example, a sigma 3 boundary that is over here, just for reference. And we think this can be also due to the nature of these other boundaries, because being made with spark plasma sintering, the sample was not fully dense. And in fact, the porosity, of course, localizes at the boundary. And if we plot the value of excess resistance as a function of coordinate along the boundary, we see that where we have pores, the resistance spikes up. So porosity is definitely part of the reason of why we see such a large fluctuation in resistance. So from this, we can also say that if we extrapolate the values that are corresponding to clean non-pore region, then we would find a value of resistance in the neighborhood of 5 mesoscale Kelvin per gigawatt that is more in line with what was reported for dense. Okay, so in summary, we have seen that we can use the FTTR technique, and in particular thermal imaging, for developing structure property relations, where we can measure one boundary at a time and figure out why and what morphological variations in this boundary are responsible for the changes in thermal conductivity that we see. And we can give an estimate of the thermal resistance with the Gibbs success method. And by doing so in silicon, we understood that there are a number of different features that can impact the estimate of excess resistance, in particular the misorientation angle that was also identified previously. And for silicon, we specifically notice the impact of interface roughness nanotwinning, and local porosity that are all seen increasing, but in different ways, the thermal, the excess boundary resistance. So with this, I would like to acknowledge all the people that contributed to the work, and thank you very much for the attention. Please don't hesitate to reach out for any question or comment about this work. Thank you.